Okay, so in the last video we saw about what kernel threads are versus user threads. Let's take a look at the differences and advantages and disadvantages. So for example, advantages of user level threads are performance. Low cost thread operations like switching threads might be a lot simpler if it does not involve the different protection domains that need to be crossed when you're talking about kernel threads. So user level threads, switching between them might be faster. Scheduling, you are in charge of basically deciding when these threads will run, so you might be able to tailor which thread gets to execute when. So if you are in control, you might be able to make better decisions as opposed to the kernel. Portability, these user level threads are easy to port. The same Pthread library, for example, exists on Mac OS X, Linux, Windows, and just about a whole bunch of operating systems have, for example, these portable threads. Pthreads stands for POSIX threads, and these are supposed to be a lot more portable than the one that we will be looking at, which is Linux specific. Okay. So a disadvantage of user level thread, for one thing, if a user level thread is blocked in the kernel, the entire process will be blocked. That is, or they can be blocked. What does that mean? That means one single thread could crash your program. So if your program consists of 2 threads, maybe 100 threads, and one of them blocks or is somehow hung up, your entire program could crash. So that's the disadvantage. You cannot take advantage directly of multiprocessing because the kernel is what assigns the process to a processor, and so you may not be able to take advantage of multiprocessing. That is, you may not be able to make your code faster. So the disadvantages, once again, to repeat, are a single thread could crash your program, and these threads in the user that's running in user space may not be faster, may not make your program faster. Okay. So there are disadvantages. The advantages are it might be switching between them might be fast. You can decide when the threads execute, and you can probably take your C program which uses user level threads, take it to another machine, and it'll probably work, probably compile and run. Okay, so let's take a look at how much time you need to do, for example, a fork. And that is, I'm sorry, let me just back up. When I say null fork, that is, all that means is how much time does it take to start up a thread. So this is not the same as the fork function call that we've been using in Linux. This is actually a fork that says start up this new thread and don't do anything, just exit. So this takes, and this is really old numbers, but these are just here for comparison. Microseconds, that is definitely an older scale. These days it'll probably be a much smaller number, but let's just go with this. Let's just say this is just for comparison. These are actually from an older system. So for just to start up a thread and exit, a user level thread will take 30 microseconds, as opposed to kernel thread, which might take 1,000 microseconds. So one that we will be using will be this, although it doesn't take this long these days. In comparison to user level threads, it is about 30 times slower, the kernel threads, which is what we're going to use. Compare this to an actual fork, and so this is the number for an actual fork. This might take 10 times longer than a kernel thread. So an actual fork could take up to about 10 milliseconds on this particular system. Of course, if you timed it now on modern computers, they're just growing faster and faster. It's probably a lot less than this. But just to compare, these are roughly the scale. So you can see that user level threads are probably the best ones. If you're worried about the speed up of starting threads, then the user level threads are definitely faster. The amount of time that you need for a signal wait is also the same thing. Much faster on user level threads, slower on kernel threads, and then even slower on processes. So this is just a comparison, a rough comparison. Basically, the idea is just that user level threads are faster for starting up a thread for a signal wait response. Okay, now let's take a look at a couple of thread models. We will be using one-to-one thread models, and so the other models that we will talk about are not things that we will use, but you might want to have a rough idea of what they are. So in a one-to-one thread model, each user level thread maps to kernel thread. So these are all for user level threads. We will be using a kernel thread directly, so actually we don't really even have to worry about the thread model. So what are examples? Windows 95, Windows 98, Windows NT, 2000, XP, all of those things have user level threads that map to kernel threads. So if you were to take Pthreads, which we talk about very briefly in the lab, and if you were to use the Pthreads on Windows, you're pretty much guaranteed that each thread will run on a single kernel thread. So, but that's not always the case, as we will see. So the one-to-one model is that you write your code using user-level threads, but they execute directly onto individual kernel threads. So let's just take a look at the difference. So actually, I don't have a slide for the other options. There are other options. The idea there is that many user threads might be running on one kernel thread. So I don't have an example of that, but if you've ever used the Oracle's Solaris operating system, that allows you to have multiple user threads running on one kernel thread. And so we won't run into that situation, so I don't have it here for you. Okay, some of the issues that we will run into in threading. Let's say you start up a new process using fork, and then in that new process, you start up multiple threads. And then one of the threads, if you exec, what you can do, what exec does is it replaces the process completely with some other program. Well, then you might wonder, well, what will happen if you do a fork and then have multiple threads and one of them doesn't exec? Do all the other threads just stop? Turns out, no, it doesn't. Okay, so you can try this out for yourself, although it's not something that I'm going to ask you to do. It's one of those things that very complicated. You have to, it's quite involved, and so it's not something that we will directly tackle. But definitely, if you want to try it out, go ahead. Okay, so then also what happens if you want to cancel a thread? What happens if you get a signal? Should that be received by just one thread or by all the threads in a single process? So these are tough questions, and every system has handled these things slightly differently. And these are all things you can try out. Many systems have thread pools, and this is true in Java. You can have thread fibers, things like that in Windows. How do you protect thread-specific data? And these are all things, if you have a thread, the idea is you want to share data, but then how do you protect it? That's a question. Pthreads, we will very briefly look at in the lab, although in the interest of time, we're not going to do a whole lot with this. This is a POSIX standard, and this is a POSIX standard API for creating and synchronizing threads. So the API, that is the Application Programming Interface, specifies behavior for the thread library, but the implementation is up to the however the library is implemented. This is common in Unix operating systems. It's definitely there in Mac OS X. This is the standard way to run multi-threaded code using the Mac OS X. Also, you can get the Pthreads library for Windows as well. Although Windows definitely does have its own thread library. Very well-developed library. So it started in Windows 2000, implements the one-to-one mapping. That is, each thread, the state contains a thread ID, which is just like a process ID. It saves the register set, that is the values of all the registers, and it has separate user and kernel stacks. Just like with any process, remember the kernel runs separately, and so it has its own stack space, separate from our stack space, and it has private data storage area. Okay, so the main thing that we're going to look at is Linux threads, and so I'll do this. I'll start up on Linux threads in this next video.